You had a bit role in Apocalypse Now.
I was one of the 4 guys on a boat heading upriver with Martin Sheen to go and assassinate Marlon Brando's character.
Right, you were one of the young
I was a young sailor on this boat.
Sailor on the boat.
Yeah.
And I remember you I don't know if you confided in me, whatever.
Yeah.
It's a little late now, that you were like underage at the time. How old were you?
Yeah, so I auditioned for the movie. I was 14 years old. I got the part. They asked me how old I was in the interview. I lied and said I was 16.
Uh-huh.
They knew that I was lying, but they just hired me anyway.
So why does the universe keep looking older than it has any right to be? We point our most powerful telescopes at the earliest epochs and sometimes find, shockingly, galaxies that seem big, red, and settled, when the cosmic clock says they were born only a few 100 million years after the beginning. The intuitive assumption is that light simply carries a snapshot of what was, but light is not a neutral reporter. It gets filtered through fogs of hydrogen, bent by gravity, and translated by instruments and algorithms that favor the loudest signals. What reaches us is history already edited by physics. Here's the tension. Our cosmological models say structure builds gradually, yet some early galaxies look like they've skipped adolescence. To make sense of that, start with the observation pipeline. A galaxy's age is inferred by fitting its multi-band spectrum and colors, especially the 4000 Balmer break, but broadband photometry can be fooled. Dust reddening and strong nebular emission in young starbursts can reproduce the colors and apparent breaks we associate with older populations. Dust forms quickly when the first massive stars die. It reddens light, tricking us into thinking we're seeing older stars. Gravitational lensing can boost the brightness of rare compact systems, biasing our surveys toward the cosmic overachievers. And when you push to the detection limit, random noise scatters some faint objects into our sample, a statistical quirk called Eddington bias that makes the extreme look more common than it is. Each of these is a small nudge, but together they tilt our first impression toward maturity. Let's go deeper than misperception. Suppose some of those galaxies really did grow up fast. In the early universe, average densities were orders of magnitude higher than they are today, and the dynamical timescale ET, din, he, wan, sqrt, gr shrinks accordingly. That means gas can collapse, fragment, and convert into stars quickly, less time between cloud and cluster. Cooling in primordial and very low-metallicity gas is set first by molecular hydrogen, and, when present, HD. Once even trace metals and dust appear, fine structure lines of carbon and oxygen and dust thermal emission take over, reshaping the fragmentation scale. These conditions can tilt the stellar bursts toward higher characteristic masses in the earliest episodes, boosting luminosity per unit mass and hastening chemical enrichment, though the precise initial mass function remains uncertain. Feedback from those massive stars, winds and supernovae, both regulate star formation and drives turbulence that can funnel more gas to the center, igniting compact, intense starbursts. And if you add early black hole seeds, perhaps formed by direct collapse, accretion can briefly outpace the galaxy's own starlight, with radiation pressure clearing gas and enforcing a sudden quenching. A galaxy that burns hard and fast can look red and dead, not because it's old, but because it finished its main act early. Now comes a subtler wrinkle. Our idea of age itself gets slippery in a relativistic universe. Cosmologists mean proper time since the Big Bang measured along a comoving clock. Observers infer age from spectral fingerprints shaped by star formation histories, not by an absolute stopwatch. A galaxy that formed most of its stars in a 50-million-year burst can display spectral features similar to a system that simmered for 1 billion years. The difference lies in details like nebular emission and filling absorption lines, which are easy to misread without high-resolution spectra. Gravity adds nuance. Deep potential wells introduce tiny gravitational redshifts and alter local time rates. Too small to explain the whole effect, but a reminder that simultaneous is not absolute. Hierarchical assembly complicates the picture further. A young halo can accrete satellites full of old stars, so the starlight looks aged even as the structure is newly assembled. And then there's downsizing, the empirical fact that the most massive galaxies shut off star formation earlier than smaller ones. That sounds backwards until you account for how cooling, feedback, and environment scale, with mass in a universe where density and merger rates change with time. Even if physics lets a few systems race ahead, we still have to measure them correctly. Photometric redshifts, as a workhorse for deep surveys, can confuse a dusty, moderately distant galaxy with a pristine, very distant one. A single misidentified emission line can move an object from a nearby catalog to the early universe and back again. Limited infrared filters mean we're often guessing at rest frame optical light, which anchors mass estimates. A missing band can swing the inferred mass by a factor of a few. Nebular continuum and strong emission lines can contaminate broadband fluxes and mimic apparent continuum breaks, biasing ages high and inflating inferred stellar masses unless the models account for them. Surface brightness dimming scales, as once at Mach 4, so we preferentially detect compact, high surface brightness cores and miss the diffuse outskirts, biasing us toward systems that look structurally mature. The point spread function blends neighbors, quietly adding flux and pushing a candidate into the surprisingly massive bin. Stellar population libraries themselves carry assumptions, include binary evolution and stellar rotation, and the same data can imply lower mass-to-light ratios and sometimes older inferred ages because interactions and rotational mixing keep massive stars hot and luminous for longer. When spectra lock down redshifts and line strengths, many impossibly old candidates retreat to merely impressive. But suppose, after we clean the data and refine the models, a population remains that truly formed stars early, quenched quickly, and looks older than the clock suggests. What does that mean for us? It means our benchmark for what counts as mature is provincial. In human terms, we equate maturity with the passage of years. In cosmic terms, maturity is about entropy processed, metals forged, and potential energy converted into binding energy and radiation. Early environments compress experience. High densities accelerate collapse, low metallicities channel coolant, and frequent mergers rearrange matter on short timescales. A galaxy can cross functional thresholds: central black hole established, stellar mass assembled, star formation curtailed, rapidly, even while the universe is still an infant by absolute time. And our surveys are tuned to notice these outliers because their compactness and brightness punch through the cosmic glare. Seen this way, the contradiction isn't between data and theory. It's between our intuitive timeline and the universe's capacity for speed. So, why does the universe keep looking older than it has any right to be? Because we often mistake speed for age. Light that reached us has been biased toward compact, bright overachievers. The physics of early epochs compresses growth into brief, intense episodes, and our methods translate those fast-track accomplishments into the language of years. When we recalibrate, updating stellar models, tightening redshifts, accounting for selection effects, and embracing the dynamical reality of early structure formation, the universe doesn't secretly add years to its age. It reveals that maturity is a state you can reach quickly under the right conditions. The cosmos isn't lying about how old it is. We were asking it the wrong question, like if this was interesting, and hit the subscribe for more.